He will speak about nondemolition thermometry of a Bose-Einstein condensate in sub-nK regime. Please.
Okay, thanks for the introduction, and thanks for everybody to attend this talk. I hope you find it useful, and I hope you give me some feedbacks after the talk or in the upcoming days that I'm around. So just to give you an idea what we are going to do, we have a BEC. It's very cold. It has temperatures like a few nanokelvin or even below a nanokelvin. And we promise not to destroy this. This is quite precious for us. And we want yet to estimate its temperature with a minimum statistical error. Just to let you know that in temperature estimation, unlike probably other parameter estimations, the statistical error is actually the main source of error that actually matters. Probably even, do you hear me? Probably even more than the systematic error. And why is that? Basically, if this is the energy structure of your system, at high temperatures, there's a probability that your system is occupying all energy states. So you have some statistics. When you measure it, there is some statistics that you can use it to estimate the temperature. It's basically kind of a sensitivity to the temperature. However, if the temperature is very low, your system kind of freezes in the ground state and your statistics is very weak. So this is basically the main reason that we have a very big statistical error at low temperatures. You can look at this review paper that explains the big problems of low temperature thermometry and introduces a lot of works that people have done on overcoming this issue. So going back in the BEC problem, what do people usually do? It's basically time of flight measurements. Basically, they open the trap that is confining the BEC and allow for some expansion, and then they shine some laser beam and analyze the absorption signal of the laser beam, from which they can decide what is the momentum distribution of the BEC. And from there, they map back this momentum distribution into the temperature of the BEC, because this distribution is a function of the temperature. So these kind of measurements could be performed directly on the BEC, which has good precisions, even down to a fraction of nanokelvin. These are the records of low temperatures in the lab of Ketterle. The problem is that these kind of measurements are destructive, because you open the trap, in the end of the day, you don't have your BEC. Alternatively, people usually introduce a second species of BEC in a different trap, which I show with these red balls, and then do the same measurement now with this second species. So assuming that they have reached some equilibrium, then studying the distribution of these particles gives some hint about the temperature of the actual species that we wanted to know. These kind of measurements usually have bad precisions into few nanokelvin. They are good for, let's say, 100 nanokelvin domain. But the good point is that they are non-demolition. The problem that arises in such kind of measurements is usually the thermalization assumption. Roughly speaking, it's if you have a global system which is at thermal equilibrium, and if you look at a fraction of this system, not necessarily this would be at thermal equilibrium when you trace out the rest of the system, because of the quantum correlations that exist between the two sides of your system. So having that said, let's look what we want to do. Basically, we want to find a thermometry protocol which is non-demolition. We don't want to destroy the BEC. It's precise in the nanokelvin or even sub-nanokelvin regime. And we want a proper theoretical description of the model. We don't want thermalization assumption or weak coupling assumption or things like that. So our idea is to use the Bos-Polaron thermometry, which is dubbing a impurity particle inside the BEC. So the BEC is a one-dimensional BEC, which is confined in a harmonic trap, and it's at thermal equilibrium, and our thermometry is the impurity. So it interacts with the BEC, it relaxes to a non-thermal steady state, and in the end of the day, its position and momentum, let's say the quadratures, will depend on temperature. So for instance, if temperature is hotter, it could be, let's say the squeezing of the X quadrature could be bigger or less. And in the end of the day, we measure only the impurity, so we produce some statistics here, and we map it back to the temperature. So this is what we want to do, let's say, in the lab. However, to do this mapping of the statistic to the temperature, we need to have a proper theoretical description of the system so that we connect these statistics back to the temperature. So basically, we need the temperature dependence of the statistics. This is in general a difficult problem because we are dealing with infinite dimensional systems. Just to have a flavor, I showed the Hamiltonian of this system, which is built of the Hamiltonian of the impurity. It's like a harmonic oscillator. We have a harmonic trap. This omega is the frequency of the trap of the impurity. Then we have the Hamiltonian of the BEC. This is the free Hamiltonian. Basically, these are creation and annihilation. They are the field operators of the bosonic particles that have the bosonic algebra. And again, the potential of the BEC is also a harmonic potential, as we already mentioned. We can also have BEC-BEC interaction. So the atoms of the BEC are interacting with each other. It's a contact interaction. This is a nonlinear term, and we show its coupling with this GBB. And then in the end of the day, of course, we want to acquire information about the BEC. We have the interaction between the impurity and the BEC. So I put this GBB equal to the same one of the to the BEC-BEC Hamiltonian, so that we capture the strength of the interaction between the impurity and the BEC in this eta here. So the bigger this eta is, let's say, the bigger the interaction is between the impurity and the BEC. So this is, as I mentioned, this is a nonlinear Hamiltonian. In general, it's difficult to solve this. However, there is a experimentally relevant range of parameters where we can map this Bose-Polaron model to the Brownian motion, where the impurity here would play the role of the Brownian particle, and the BEC, or more precisely, the Bogoliubov modes of the BEC, after diagonalizing it, will play the role of the environment. So these modes of the environment now, they don't interact with each other. They just interact with the central particle, which is our impurity. And the strength of this coupling depends on the properties of your Hamiltonian. Basically, whatever you had will be given, will decide what is the spectral density of this environment. So the details of this mapping you can find in these papers. I just don't want to distract you with this Hamiltonian. My point here by putting this here is that in the end of the day, you will end up with a quadratic Hamiltonian in this range of parameters. And as already mentioned in the morning session, when you have a quadratic Hamiltonian, you know that the steady state of this impurity would be a Gaussian state, which can be properly described by the covariance matrix and the first moments, which in our case, they tend to be 0. Just one note that unlike the usual Brownian motion problem, here our interaction is between the position of the impurity, and this is kind of a quasi-momentum of the Bogoliubov modes of the environment. Because usually in the Brownian motion, you have a position-position interaction here. Okay, so this Brownian motion is a very well-studied problem in open quantum system community. And I don't explain how you can find this covariance matrix. Basically, you do the quantum Langevin equations, and in the end of the day, you can find what is the steady state covariance matrix. Okay, perfect. Then once you have this steady state covariance matrix, you can find it analytically. Well, you have analytical description. Maybe you have to do some numerics in the end of the day. And then you can look how, for instance, the squeezing in the position depends on the temperature of the BC. So very good. Then you do the measurements and you map it back to the temperature. So this is not, however, what I'm going to talk about. Let's say this is given. I want to somehow quantify the precision of this kind of mappings. So if you want to know more about such mapping, you can see this paper. So let's define what is the error that we care about. We look at the relative error, and we quantify it through the error propagation formula. Basically, the error is proportional to the uncertainty. So given a measurement on the basis of some observer like O hat, this error is basically the uncertainty in the outcomes of this observable divided by the temperature susceptibility. So it kind of makes sense because the bigger the uncertainty is, the bigger the error is, and also the bigger the response of the observable to temperature is, the smaller the error is. And then from central limit theorem, we know that if we repeat the measurements, then we have a square root enhancement with the number of measurements. Okay, then a very interesting question would be if we can make this error as small as possible. We know that this is not possible because of the Kramer-Rao bound, which says that this relative error is bounded by the inverse of the quantum Fisher information. Then another interesting question would be, is there an observable which saturates this bound? The answer is yes. So there are a lot of works that have already done this for Gaussian formalism. Probably the first one would be by Alex Monras, and then by Jiang. And then recently, Rosanna Nichols and the group of Gerardo Adesso, they have extended this to multi-parameter estimation in Gaussian formalism. However, for our case, because we are only measuring the temperature, we stick to the paper of Alex Monras. Basically, details are there. You can go and find it. If you have the covariance matrix and if you have its temperature dependence, basically you can quantify the error very easily. Okay, so we have basically everything. Let's look at some examples. So in our case, sorry, before going to examples, in our case, we can find that the optimal measurements are a linear superposition between the position and the momentum of the impurity. So these couplings that appear here, they can depend in general on the parameters that define your problem. They also depend on the temperature itself. So we know, for instance, in the case that we have a very weak coupling, these two constants will be the same as those that appear in the Hamiltonian of the impurity. Okay. So just to have a flavor, we look at a specific example. This is not limited. This study is not limited to this, but okay, we should do some numerics. We look at a BSE of potassium atoms and an impurity of ytterbium atom. And we look at the minimum error, which is measured by these symmetric logarithmic derivatives, this observable which appears here, for different coupling strength. For comparison, we also put a scenario where we assume that the impurity would have thermalized with the BEC. This is not happening, but this is just for comparison. And the temperature range that we are looking at is from 200 picokelvin to 2 nanokelvin. Notice that this is a logarithmic scale. So the first thing that we see is that stronger couplings worsen the precision. So this eta is somehow quantifying the strength of the interaction. And then we see that we can have a relative error. This is for single shot, by the way. So we can have a relative error below 14% with only 100 measurements. For instance, if you look at this case with weaker couplings. And then finally, the thermalization assumption is not correct. As you see, the behavior is different from thermalization assumption, especially if you have a stronger couplings. This is deviating quite a lot. Okay, so as I mentioned, this precision is achieved by performing this weird kind of measurement in a superposition of position and momentum. This is probably not possible in practice to do. What can we do if we could measure only position or momentum of the impurity? This is more practical, basically. So here I'm looking at this problem, and I'm benchmarking this against the optimal measurement that I can do. So these black curves are the optimal ones. The blue curves are position measurements, and the red ones are that of the momentum. So the first thing that we see is that position measurements are always performing better than the momentum ones. And we see that we can still have relative errors below 18% by measuring the position, yet by slightly more number of, 400 times measurements. For before we had only 100 measurements. I think it's still reasonable. And then another thing that we notice is that as you increase the strength of the impurity BC interaction, the performance of position measurements are getting closer to the optimal one. This is not actually because the position is performing actually better. It's because as I already mentioned in the previous slide, the optimal measurement is getting worse, such that it gets closer to the position. Okay. Just a quick note. Maybe you have seen previous works that predict strong coupling can enhance thermometry precision. However, I was just saying otherwise. So what is the reason? This is a previous work where it's predicted that strong coupling is useful for thermometry. Actually, the reason is that the temperature regime that we are looking at is not qualified, let's say, as a low temperature regime. So if we continue going to smaller and smaller temperatures, we will see that we reach a regime where increasing the strength of the interaction will eventually start to be useful for thermometry. However, the problem is that this is not basically in this regime the relative error is very big. So notice that this is a logarithmic scale. So the relative error is 10 to the power of 40 or something. So in order to have a enhancement by the strong coupling, you have to go to regimes where actually the precision is very bad anyway. So let me introduce you the people who collaborated with me in this work: Aniello Lampo and Christos Garalambos from ICFO, Luis Correa from Nottingham, Miguel Angel Garcia March from ICFO, and Maciek Lewenstein from ICFO. Just to wrap it up, so we can have a relative error below 14% with 100 number of measurements. This is achieved by doing this weird kind of measurement in a superposition of position and momentum. We can have suboptimal measurements of position, which can have relative error of 18% with 400 measurements. Probably a future direction would be to look at extensions of this problem in two-dimensional and three-dimensional BCs. What would probably change in these cases is the spectral density of the environment when you map your system to the Brownian motion. Another direction would be exploring role of quantum correlations by studying double impurities when you have two impurities or multiple impurities, and see, for instance, if you have an interaction also between the impurities, apart from the correlation that is created thanks to the interaction to the environment, the interaction between the two impurities also can create some kind of correlation. So you can see more details of this work in this paper and in general about quantum thermometry in this review. Thank you for your attention.
Questions?